Hello, everyone. My name is Anindya. So, welcome to the series of lectures on the Myhill-Nerode theorem. Uh, a little bit about me. So, I'm currently an assistant professor in computer and information science at the University of Pennsylvania. And in the past, I was on the faculty at Northwestern. Before that, I did my postdoc at the Institute for Advanced Study and IMAX. Before that, I finished my PhD from Berkeley in 2013. And I finished my undergraduate studies in India, which is where I grew up. So my current research mainly focuses on the role of randomness in computation. And increasingly, of late, I have also been looking at the mathematical foundations of inference, learning, and broadly speaking, statistics as well. Um, so the reason I am in theoretical computer science, well, there are many, but maybe above all, the reason is that I believe computation holds a fundamental promise as a lens to look at every other science. It's a way of understanding how, in a bottom-up fashion, simple processes can give rise to very complicated phenomena. And towards that, I believe theoretical CS is a very foundational way of understanding these processes. Coming back to the agenda for the series of videos, uh, so the goal of this series of videos is uh, oops, uh, the goal of the series of videos is to provide a syntactic characterization of the class of regular languages, which you have already seen in the previous lectures. What I mean by providing a syntactic characterization will be that we will, so far, when we have discussed regular languages, we have seen this as a class of languages which are accepted by a finite automata. But you'll see like there's an entirely different way of talking about regular languages, which does not at all make any reference to a finite automata. And this will be the goal of the Myhill-Nerode theorem, which will prove in this series of lectures. And then the Myhill-Nerode theorem will also give us a way to compute the best DFA, the smallest DFA for any regular language. Okay, so this, in other words, given there's a regular language, will show how there's a unique best DFA to compute that language and also a way to find such a DFA. And so as an outline for the rest of these videos, the first one was this video, the introductory video. In the next video, I will talk about equivalence relations. So this is a very basic kind of mathematical object in set theory, and which you might have encountered in discrete math before. So I'll recall the basics of equivalence relations and what we need of them. And the goal of the third video would be to prove the so-called Myhill-Nerode theorem, in which we'll heavily use the notion of equivalence relations. And the fourth video will use the Myhill-Nerode theorem, or rather the tools that we will introduce to prove Myhill-Nerode theorem, in order to give an algorithm which, given any DFA, will find out the smallest DFA which accepts the very same language. So that will be our agenda. So thank you. Hello, everyone. So this is the second video on the topic of Myhill-Nerode theorem. So in this video, the goal is to understand one of the fundamental constructs in set theory, namely an equivalence relation, which will prove to be very useful in our study of the Myhill-Nerode theorem. So before defining what an equivalence relation is, let's just recall what a relation is. So for a set A, capital A, let's call it the ground set, a relation R is nothing but a subset of the Cartesian product of A with itself. In other words, a relation R is nothing but a subset of ordered pairs of elements which come from the ground set A. Now, as you can see, the notion of a relation is extremely general, and as such, given it is so general, it's essentially unuseful. So we impose a few more restrictions on the notion of a relation to make it useful. And we arrive at the definition of an equivalence relation. So what's an equivalence relation? So an equivalence relation is nothing but a relation R, again on the ground set A, which satisfies three axioms. First is the axiom of reflexivity, which just says that whenever consider any element little a in the ground set A, then A comma A is in the relation R. So among other things, this implies that an equivalence relation can never be empty. It at least has some elements. Second is the notion of symmetry, which says that if A comma B is an element of R for elements A and B belonging to the ground set capital A, then B comma A is also an element of R. So in other words, what you get here is that even though we define relation R to be a subset of ordered pairs over the ground set capital A, as far as an equivalence relation is concerned, the order is immaterial. Okay, and the third axiom is the axiom of transitivity, which says that if A comma B is an element of R and B comma C is an element of R, then A comma C is also an element of R. So that finishes the definition of an equivalence relation. And equivalence relations can be found all over in mathematics, and certainly in discrete math, but also in continuous math. And let's see an example of an equivalence relation just to make sure that we're on the same page with this definition. So one particular example is the notion of connectivity in undirected graphs. So let G equal to V comma E be an undirected graph. So what do I mean by this? I mean that V is the set of vertices and E is the set of edges in this graph. And remember, the graph is undirected. So now for this graph G, we define the notion of a relation R sub G. This will be an equivalence relation, which we define now. It will be defined on the set V. The ground set is the set V of vertices. And X comma Y, two vertices X comma Y, are said to be in this relation R sub G if in the graph G there's a path from X to Y. So there's a way to go from X to Y in the graph G. And the claim is that this relation R sub G for an undirected graph G is an equivalence relation. And we now verify the axioms of an equivalence relation. So let's verify the first axiom. The first axiom is that of reflexivity. So which is just we need to verify that whenever X is a vertex in the graph, X is an element of V. Let's verify that X comma X is in RG. And this is easy to check, right? Because whatever be a vertex X, there is always a path from X to X. Because you can always go from X to X for a path of length 0. Okay. So reflexivity, the axiom of reflexivity is satisfied. The next axiom is that of symmetry. So we need to verify that if X comma Y is in RG, then Y comma X is in RG. And this is again easy to check because if there's a path from X to Y in a graph G, then there's also a path from Y to X, because you can always retrace the steps in an undirected graph. And this is where we use the notion of undirected, the graph being undirected, crucially. This is not true for directed graph. And the final is, finally, we check the notion of transitivity, which just says that if X comma Y, so we need to verify that if X comma Y is in RG and Y comma Z is in RG, then X comma Z is in RG. And this is again easy to check from the definition of a path. If there's a path from X to Y and there's a path from Y to Z, then there's also paths from X to Z. You can go from X to Y and then Y to Z. Potentially there's a simpler path, but there's certainly you can go from X to Z. So this verifies that the relation R sub G is also transitive. And there's in summary, R sub G is an equivalence relation. Having seen the notion of an equivalence relation, now let's associate something called an equivalence, a particular construct called an equivalence class can always be associated with an equivalence relation. So let's see what it is. So let R be an equivalence relation on a ground set capital A. Then for any element X in A, we can define an equivalence class called X sub R or bracket X sub R. So this thing, which is defined to be the set of all elements Y such that X comma Y is in R. So the equivalence class of X in context of the relation R, which we denote by the square bracket X with a subscript R, is a set of all elements to which X is related. Okay. And okay, so first of all, this will also explain where the name equivalence relation comes from. So the first observation is that if X and Y are related, if X comma Y belongs to R, then the equivalence class of X is equal to the equivalence class of Y. Again, I'm not constantly saying equivalence of class of X with respect to R. With respect to R is understood in this context here, but so I'm not going to always say that. But the main thing is that if X and Y are related, if X comma Y is in R, then the equivalence class of X equals the equivalence class of Y. Why is this true? So observe as a standard, observe as is, pardon the interruption. Pardon the interruption, please. Sorry. So let's get back to this thing. So observation, if X comma Y is an element of R, then we want to show that the equivalence class of X and Y are the same. To show this, observe that it suffices to show that the equivalence class of X is contained in the equivalence class of Y. Note that if we manage to show this, then we can also show by symmetry that equivalence class of Y is contained in equivalence class of X, which would thus prove that equivalence class of X and equivalence class of Y are identical. Okay, so how do we show that the equivalence class of X is contained in the equivalence class of Y? Well, so consider any element Z in the equivalence class of X. This is the same as saying that X comma Z is in R. Now, by definition, X comma Y is in R. So by the symmetry axiom of equivalence relations, Y comma X is also in R. And then by the transitivity property of an equivalence relation, by combining X comma Z is in R and Y comma X is in R, we derive that Y comma Z is in R, and thus Z is in the equivalence class of Y. So any element Z which is in the equivalence class of X is also in the equivalence class of Y, thus showing that the equivalence class of X is a subset of the equivalence class of Y. By symmetry, you can also show that the equivalence class of Y is contained in the equivalence class of X, which will show that the equivalence class of X and Y are identical. So in other words, now you can see why the name equivalence relation comes. It says that if X and Y are related, X and Y belongs to X comma Y belongs to R, then the set of all elements which such that X comma Y is in R, if we define this as the equivalence class of X, then whether you consider now define the equivalence class of Y, these are all same sets. So somehow one should interpret this as saying that up to the relation R, this elements, the element X, the element Y, and every element contained in the related to X or related to Y via R are all equal, really. So that's roughly the notion of where the name equivalence relation is coming from. Okay. Now, a very important property is that an equivalence relation R induces a partition on the set A in the following manner. If you consider this for every element X in the ground set A, if you consider the equivalence class of X, this defines a set of elements. This system of sets, this collection of sets, is a partition. It partitions the whole universe, ground set A, into disjoint subsets whose union spans A. Okay, so it partitions A. How do we, so let's check that this is true. Let's verify that this is true. So to verify that some collection of sets is a partition, what do we need to verify? The first thing we need to verify is that every element belongs to at least one collection. Well, that is easy to verify because the element X always belongs to the equivalence class of X. So if you consider the collection of sets, which is given by the equivalence class of X as X ranges over A, it certainly covers every element. And now we need to verify that this collection is disjoint. So suppose it's not disjoint. So suppose consider two sets, consider two elements X and Y such that the equivalence class of X and the equivalence class of Y intersect somewhere. So let Z be an element which is in the equivalence class of X and the equivalence class of Y. What does that imply? That implies that X comma Z is also in R and Y comma Z is also in R. But then by transitivity, by applying symmetry, you will get, by applying symmetry and transitivity, you can easily derive that X comma Y is in R, which by our earlier observation, namely this observation, the one I'm highlighting in yellow, shows that the equivalence class of X and the equivalence class of Y are identical. So it means that if any two sets in this collection equivalence class of X intersect, then they're basically the same sets. Or in other words, of course, so in other words, no two sets intersect non-trivially. If two sets intersect at one point, they are the same set. So if the only way equivalence class of X and equivalence class of Y share an element is because they're the same sets. Or in other words, you can think of calling some set equivalence class of X is just a renaming of calling it equivalence class of Y. Okay. So this proves that the equivalence equivalence relation R induces a partition where the sets of the partition are given by equivalence class of X as X ranges over A. And again, it's important to emphasize that many sets in this collection of sets equivalence class of X as X ranges over A are identical, are the same. So they're just renamings of each other. So we might be naming a set more than once, calling it equivalence class of X and also calling it equivalence class of Y, if X and Y are related. But up to renaming the sets and naming several sets at the same time, naming the same set several times, these sets form a partition. So there's a picture, like, if the red thing is the universe A, the ground set A, then you can think of equivalence classes as partitioning the ground set A, let's say in this example, into 5 parts. The first one is the ground set equivalence class of X1, which I just made yellow. The second part element of the second set in the partition is the equivalence class of X2, which I now did yellow. Similarly, equivalence class of X3, X4, and X5. So for example, the one I'm making orange right now consists of all elements. It's the equivalence class of X4, which consists of all elements such that X4 comma, it consists of all elements Z such that X4 comma Z is in R. Okay. Now, equivalence relations for our purposes can be divided into 2 parts, and this is very important. Those equivalence relations which induce a finite number of equivalence classes, for example, in the picture here that we have drawn, this equivalence relation has 5 equivalence classes. And then there are those equivalence relations which have infinite number of equivalence classes. This distinction is going to be very important for us. So of course, for example, in a graph, the graph equivalence relation RG that we saw earlier, this is a finite equivalence relation, partially because the set itself is finite, so you cannot have infinite number of equivalence classes. If the ground set V is finite, you cannot have infinite number of equivalence classes. But as we are going to see examples of equivalence classes, equivalence relations such which induce infinite number of equivalence classes. And this distinction between finite and infinite is very important in the context of Myhill-Nerode theorem. The final thing I need of this final definition I need is the notion of refinement of partitions. In particular, if R and R prime are two equivalence relations on the set A, such that whenever x comma y is in R, x comma y is also in R prime. So any two elements which are related in R, they're also related in R prime. Then we say that R is a refinement of R prime. The reason we say this is that so let's see an example. Let's see example of two equivalence relations, R1 and R2, and observe that in this picture, R1, whenever two elements are related in R1, say x1 and x2, say any two elements which are related in R1, let's say this element and this element, actually, let me use a different marker. So let's say an element, these two green elements I'm marking now, they're related in R1 because they belong to the same equivalence class in R1, namely they're both related to x1. Then they're also related in x2. Okay. Of course, the reverse is not true. For example, the elements x1 and x2 are both in the same equivalence class in R2, but they're in different equivalence classes in R1. And that is why we say that an equivalence relation, whenever this thing holds good, we say equivalence relation R1 refines equivalence relation R2. The reason we are calling it a refinement is because it's inducing, the equivalence relation R1 is inducing a finer partition than R2. Okay. So for example, okay. And so an obvious corollary just of this definition is that if equivalence relation R1 refines R2, then the number of equivalence classes in R1 is at least as large as the number of equivalence classes in R2. The reason being that you're only making the partitions finer. R1 only makes partitions in R2 finer. What R2 does is that it may two partitions which are different in R1 may coalesce in R2. For example, that's what happened to the partitions in R1. Okay. And so it might happen that equivalence relation R1 is infinite, has an infinite number of equivalence classes, and equivalence relation R2 has infinite number of equivalence classes. And then this corollary might not make sense, like what do we mean by the number of equivalence classes? But as long as at least R2 has finite number of equivalence classes, you can always say that the number of equivalence classes in R1 is at least as large as that of R2. R1 might have infinite number of equivalence classes, but if R1 also has finite number of equivalence classes, then the number of equivalence classes in R1 is at least as large as that of R2. And this is basically just the obvious corollary of the definition of a refinement of equivalence classes. So with that, let me conclude this lecture, but let's just recap what we saw. So we started with the notion of equivalence relation. We defined what an equivalence relation is as basically a relation which satisfies three axioms: reflexivity, symmetry, and transitivity. Then we defined the notion, we saw an example of an equivalence relation, namely the connectivity in an undirected graph. We followed it up with seeing the notion of equivalence classes, which are induced by an equivalence relation. And we saw how an equivalence class, an equivalence relation via equivalence classes induces a partition of the ground set A. We said that there are two different kinds of equivalence relations, those which induce finite number of equivalence classes and those which induce infinite number of equivalence classes. And this distinction is important, going to be important for us. And we ended with the notion of an equivalence class refining another equivalence class and what it means for the number of equivalence classes induced via the first equivalence relation vis-a-vis the second equivalence relation. So let's conclude the lecture now. Let's conclude this video now rather. Thank you. Hi everyone. So this is our third video on the topic of Myhill-Nerode theorem. And in this video, we are going to actually prove the Myhill-Nerode theorem. So in order to prove this theorem, I'll first define an equivalence relation in the context of any language L. So the language L is not necessarily a regular language, but an arbitrary language L. And in context of this, we can define an equivalence relation, which we denote by R sub L, which is defined as follows. So two strings X and Y are said to be in RL if, doesn't matter what string Z you choose, if you append Z to both X and Y, then either both XZ and YZ are in L, or neither XZ nor YZ is in L. So means maybe it is the case that suppose you choose Z equals 0, then you can say that either both x0, y0 are in L, or neither x0, y0, neither x0 nor y0 are in L. Okay. Similarly, maybe if you choose, for example, you can also choose Z to be the empty string. And then you get that if x comma y is in RL, then either both x and y are in L, or both x and y are not in L. Okay. So in some sense, with respect to the set L, doesn't matter what string Z you choose to append, the membership of xz and yz in L have the same value. Either both of them are there, or both of them aren't there. Okay. So this is the definition of the equivalence relation RL. So let's verify that this is indeed an equivalence relation. So the reflexivity is trivial to see, right? X comma X is always in RL because for if I just substitute Y equals X, then trivially for every Z in sigma star, either both XZ and XZ are in L, or both XZ and XZ are not in L. Of course, either XZ is in L or XZ is not in L. So that trivially implies the reflexivity property. The symmetry property is also trivial because, again, if you look at the definition of the relation RL, the definition is symmetric with respect to X and Y. So the precise order of X and Y is immaterial. And finally, the transitivity is again very easy to check. So suppose you know that XY is in RL and YW is in RL, then we seek to prove that X comma W is also in RL. But to see this, suppose if X and Y are in RL, then it means that for every string Z in sigma star, again, either both XZ, YZ is in L, or neither XZ nor YZ in L, YZ is in L. Similarly, because so again, let me just repeat this. So if Y is in RL, then it means that either both XZ is in L, YZ are in L, or neither XZ nor YZ are in L. And similarly, if YW is in RL, then it means that either both YZ and WZ are in L, or neither YZ nor WZ are in L. Okay. But together from these two conditions, 1, 2, and these two next 1, 2 items, you can derive that either both XZ comma WZ, they are both of them are in L, or neither XZ nor WZ are in L. Okay. This, by the way, is just the definition of X comma W being in R sub L. And thus you get that, thus you get that if XY is in RL and thus you get that if XY is in RL and YW is in RL, then you get that XW is also in RL, thus proving the transitivity property. So for any language, and this did not require this definition, notice that our proof did not require L to be a regular language. This can be any language L over any alphabet sigma. Okay, so this is a general definition. Now, we will not directly use this definition right now, but let me just make one definition. Since given we have defined R sub L, it is that if you choose any language L over sigma, with respect to this language L, we say two strings x and y are distinguishable if x comma y is not in RL. So what this means is that if we say two strings x and y are distinguishable, then it means that there exists some z such that xz is in L and yz is not in L, or xz is not in L and yz is in L. So this is equivalent to saying that x and y are distinguishable. So let's just remember this definition. Okay. So far we were talking about arbitrary languages L. Now we will think about regular languages, but before we do that, let's define yet another equivalence relation. Now, not with respect to a language L, but a DFA M. So let M equals Q sigma delta Q naught F be a DFA. Then with respect to this DFA M, we define an equivalence relation R sub M, again on the set of strings over sigma. Okay, so similar to just like RL was an equivalence relation over strings over sigma, so the underlying alphabet sigma. Again here, the relation R sub M is also over strings over sigma. The equivalence relation is defined as follows. X comma Y is in Rm, R sub M, if the state reached by M when you start at the state Q naught and on input X is same as the state reached by M when you start at the initial state Q naught and read the input Y. So in other words, X and Y belong to the relation R sub M if the automata starting from its initial state on reading X and on reading Y reaches the same state. Okay. Again, so this is the definition of the equivalence relation. And again, let us verify that this is the relation we defined just now is an equivalence relation. And it is easy to check all the three properties of equivalence relations. The first property, reflexivity, is again trivial because x comma x is in Rm. Why? Because you just require that the state reached by the automata M on input X is same as the state reached by automata M on input X, because Y is now X. And that is trivially true. That is tautologically true. So reflexivity is trivial to verify. Symmetry again is trivial to verify because our definition of the relation R sub M is symmetric with respect to the strings X and Y. We are not, this definition itself is symmetric with respect to X and Y. And transitivity is again the same because if you know that X comma Y is in Rm, if you know that X comma Y is in Rm, let's say, and Y comma Z is in Rm, then you know that the automata M on reading the input X and reading the input Y takes you to the same state. But you know that automata M on reading input Y and reading input Z also takes you to the same state, which means that the states reached by M on input X and input Z is the same, which thereby implying that the pair X comma Z is in Rm. Okay. Thus, the relation Rm also satisfies transitivity, proving that Rm is an equivalence relation. Okay. Now, one thing about relation Rm is that the number of classes, equivalence classes, given by the equivalence relation Rm is at most the number of states in M. In other words, if M is a finite automata, then the number of equivalence classes induced by R sub M is finite. It's some fixed number. And let's just observe that this is true. This is because when you're defining an equivalence relation, when you're defining the equivalence relation Rm, then two strings belong to the same equivalence, two strings belong to the same equivalence class, provided the automata M takes them to the same state. And thus the equivalence classes can be indexed by the states of the DFA. But the DFA has only a size of the DFA has only size of q many, capital Q many states. And thus the number of equivalence relations, the number of equivalence classes, I'm sorry, in R sub m is at most the number of equivalence, is at most the number of states in the DFA M. The reason I keep saying at most is because observe that there might be strings, there might be states rather in the DFA which are not reachable, in the sense that there is no string which starts from the initial state and takes you to that state. So that is why I keep saying at most. But if all states are reachable from the initial state, then the number of equivalence classes induced by Rm is precisely the number of states in M. Okay. But the high level thing you need to remember is that the equivalence relation Rm always has finite number of equivalence classes. So now, so far we have seen two equivalence relations, R sub m and R sub l. R sub m is defined with respect to any finite automata m, and R sub l is defined with respect to any language L. The next thing we prove is that if M is a DFA and L is the language of that DFA, then R sub M, the equivalence relation R sub M, refines the equivalence relation R sub L. Okay. How do we prove this? So suppose we start, so to prove that this is a refinement, R sub M refines R sub L, you have to show that if x, y belongs to Rm, then x comma y also belongs to RL. Well, what is the definition of x comma y belonging to Rm? That means that the DFA M on input x reaches the same state as the DFA M does on input y. But given the input DFA M has reached the same state called, let's say, Q on reading inputs x and y, that means that if the DFA M reads the input xz, it will reach the same state as it does on reading the input yz, right? Again, let's see. So suppose, like, there's the state Q naught, you read x and you reach the state Q. And similarly, you read y. This may not be visible very well, so let me redraw this again. Q naught Q. So if you read the input x, the DFA reaches Q, and you read the input y and you reach the same state Q. That is the definition of x and y belonging to Rm. But that means if you read the input xz, what is the state that that the DFA will reach? Well, first it will read Q, start from Q naught, read input x, reach Q, and then read string z and reach potentially some other state P. But then observe that if the DFA M reads the input yz, then again it will first read y, go to state Q, then read z and go to state P, which implies that on reading input xz and reading input yz, you reach the same state, which means either both xz and yz are accepted by the DFA, or neither xz nor yz is accepted by the DFA M. This implies that x comma y is in RL. Okay, and thus if x comma y is in Rm, it is also in RL, showing that the equivalence relation Rm refines the equivalence relation RL. An immediate corollary is that since the equivalence relation Rm refines the equivalence relation R sub L, where L is, remember, the language of the DFA M, that means that if L is a regular language, then RL has finite number of equivalence classes. That is because the relation Rm has finite number of equivalence classes, Rm refines RL, thus RL will also have finite number of equivalence classes. So you get that if L is a regular language, RL must have finite number of equivalence classes. Turns out the converse is also true. Namely, the converse is that if RL has finite number of equivalence classes, if there's any language L such that RL has finite number of equivalence classes, then L is a regular language. So so we'll prove this converse now, but does we get that if L is a regular language, then R sub L has finite number of equivalence classes and vice versa. This is referred to as the Myhill-Nerode theorem. And if you think about it, this is providing a complete characterization of regular languages. It just says L is a regular language if R sub L has finite number of equivalence classes. Observe that R sub L, the definition of R sub L, doesn't require any reference to underlying automata. So potentially one could have imagined that, I could have, without defining automata, I could have just defined regular languages as the class of languages L, where R sub L has finite number of equivalence classes without ever referencing automata. Turns out the automata definition, which is more like an operational definition, is equivalent to the syntactic definition. Okay, it's a beautiful characterization. And just, let me just mention that such characterizations are not known for larger classes of languages. And indeed, in some sense, the Myhill-Nerode theorem tells you both the power and the weakness of regular languages in one go. Anyway, let's prove the converse. So the converse is that if RL has finite number of equivalence classes, then L is a regular language. So thus we want to show that if RL has finite number of equivalence classes, then L can be recognized by a finite automata. Okay. So in some sense, the proof of the converse essentially proceeds in the only way you can proceed. Okay. So I want to show that L is a regular language. I want to construct a finite automata for L. And the only information I have is that RL has finite number of equivalence classes. So it seems like a natural choice that since RL has finite number of equivalence classes, I should somehow construct a state corresponding to each equivalence class. So that's what we do. So for each equivalence class of R sub L, let me denote this by X sub L. So the string X belongs to the equivalence class X bracket sub L. Okay. We add a state in the DFA. Okay. So for each string X, we look at the equivalence class. And for each such equivalence class, X sub L, we add a finite state. Of course, the same equivalence class can have many names, right? If X and Y belong to RL, then X sub L is an alternate name for Y sub L. So I'm saying that if X, Y belong to RL, then X sub L and Y sub L are the same equivalence classes. And so I am not going to create different states for X and Y. I'm just going to create one state per equivalence class. Now, since RL has finite number of equivalence classes, then the number of states I have created is finite. Having defined the states, let's next define what are the final or the accepting states of the DFA. The final or the accepting states of the DFA are just going to be X sub L for those X's which are in the language. So I start with a bunch of equivalents. I start with a bunch of states, create a bunch of states, and then every state which corresponds to a string, every state which can be written as X sub L, where X belongs to the language, is included as a final of an accepting state. the initial state is just the equivalence class of the empty string. Okay. And finally, we have to define the alphabet is well defined, it's just sigma. So finally, we have to define the transition function. And the transition function is just defined to be that if you're in the equivalence state, uh, if you're in the state corresponding to the equivalence class X sub L, then on reading sigma, let me actually give it, on reading sigma, you go to the equivalence class corresponding to the string X sigma. Okay. This is the construction of the DFA. But just because we have defined it like this, we have to make sure that the construction is well defined. In particular, the well definition would mean that the well defined property would mean that if two equivalence classes are the same, namely if X sub L equals Y sub L, okay, then we have to make sure that under the transition function delta, which on reading sigma takes the equivalence class of X, so X sub L to X sigma sub L, it should be the case for this definition to be well formed, that the equivalence, if the equivalence class of X and Y are identical, then the equivalence class of X sigma and Y sigma should also be identical. Okay. Otherwise, the definition, otherwise, not a well-defined property. Delta is not well-defined because if X sub L and Y sub L are the same, then that means I can call the state X sub L or I can also call the state Y sub L. But then under the transition function reading sigma, you should go to the same state. That means X sigma sub L should be equal to Y sigma sub L. So we should make sure that this is true. Otherwise, our definition doesn't make sense. So let's verify this. And this is actually quite easy to verify. If X sub L equals Y sub L, then it's equivalent to saying that X comma Y belongs to RL. This means that I can take any string Z, and if I append the strings sigma Z to X and sigma Z to Y, they should both be in L or they should both not be in L. So I'm appending the string sigma Z to both of them. But I can read the string X sigma Z as appending Z to the strings X sigma and Y sigma. And thus I have the property that if I append Z to X sigma and Y sigma, either they're both in L or neither is, which is equivalent to saying that X sigma comma Y sigma is in R sub L, and thus showing that the equivalence class of X sigma and Y sigma with respect to L is the same. And thus our definition, the thing we needed to confirm, is true. And thus our definition of the automata, this definition of the automata, it's well defined. Okay, this is a well-defined automata. So having given that we've defined the automata, now let's verify that the language of this automata is indeed L. And this is again easy to verify. It's basically a simple induction. So to verify that L equals L of the automata we constructed, call it M. Observe that if I start at an equivalence class X, delta X, read the symbol sigma, I go to the state corresponding to the equivalence class X sigma sub L. Now, suppose our input string X equals X1, X2, Xn. The initial state the automata is in corresponds to the equivalence class epsilon sub L. After reading X1, by definition, we will go to the equivalence class X1 sub L. We'll go to the state corresponding to the equivalence class X1 sub L. After reading X1, X2, well, I'm in state X1 sub L. I read the next symbol X2. I go to the state X1, X2 sub L, and so on. So inductively, after reading X1, X2, Xn, the automata is in the state X1, X2, Xn sub L. Okay. And recall, F consists of Y sub L, where Y belongs to L. So if X1, X2, Xn, actually, let me just, sorry, actually this, let me explain this in a little more detail. So after reading x1, x2, xn, the automata is in the state x1, x2, xn sub L. Okay. And let me actually just do this part in a little more detail. Sorry about that. So the automata is in the state x1, x2, xn sub L. We recall the set of accepting states is YL where Y belongs to L. Okay. So now we want to show that the string x1, x2, xn is accepted by this automata if and only if if and only if x1, x2, xn belongs to the language. So one direction is trivial, right? If x1, x2, xn belongs to L, then clearly the state x1, x2, xn L belongs to F. That is by definition of F. And thus x1, x2, xn is accepted by the automata. In the other direction, suppose x1, suppose you know that suppose the string x1, x2, xn, suppose the string x equals x1, x2, xn is accepted by M. Suppose this is true. Okay. Then what happens? Well, if it is accepted, that means that x1, x2, xn L equals YL for some Y in L. Or in other words, this is equal to saying x1, x2, xn Y. Let me actually just call it X really. Is in RL. Okay. But this means that for all Z, either both XZ, YZ are in L or neither is. Instantiating Z to the empty string, we get that either both XY is in L or neither X nor Y is in L. But observe, we already know that Y is in L, which implies that X must be in L. So we logically conclude that X must be in L. And thus, if on input X, the automata we just constructed reaches an accepting state of the automata, it must be the case that the string X belongs to the language. And thus the language of this automata is precisely the language L. Okay, which concludes our proof. Okay, so let me just recap because this was some long proof. So let me just conclude what we did. Okay, so we were trying to show that if RL has a finite number of equivalence classes, then L is a regular language. And to do this, what we did is we took the equivalence classes of RL with respect to RL. For each equivalence class X sub L, we constructed a state in the automata. Then we defined a set of final states to be those states which correspond to equivalence classes of accepting strings. And again, like this little argument at the end should tell you that if there's one accepting string in an equivalence class, if there's one, this little argument that we showed in the end should tell you that if there's one accepting string in an equivalence class, then all the strings in that equivalence class belong to the language. If there's one string which belongs to the language in an equivalence class, all the strings belong to the language. Anyway, so we defined a set of final states to be the set of those states which consists of which correspond to equivalence classes consisting of strings in the language. The initial state corresponds to the equivalence class of the empty string, and then we define the transition function which takes the equivalence class of X, or the state corresponding to the equivalence class of X, to the state corresponding to the equivalence class of X sigma on the input sigma. We confirmed that this definition is well meaningful. We made sure that this definition is consistent, it's well defined. And after having done that, we showed that once we've constructed this automata, then starting from the state corresponding to the empty string, which is the initial state, if you read the input X, which I call X1, X2, Xn, afterwards, like I excise the symbol in the ith bit, then the equivalence class reached by the automata corresponds to the state of the equivalence class of X. Okay. And then we showed that thus it means that if a string belongs to the language, it lands up in an accepting state or final state of the DFA. And if X does not belong to the language, then it does not land up in the final state of the DFA, thus concluding the proof. So this finishes the proof of the Myhill-Nerode theorem. A corollary is this. We already know that R sub M, if M is a finite automata, if let M be a finite automata, and L be the language of the automata, we have already seen that R sub M refines R sub L. In other words, the number of equivalence classes in R sub M is at least as large as number of equivalence classes in R sub L. On the other hand, the converse part of the Myhill-Nerode theorem showed that if there is a finite, so we get let M be a finite automata and L equals L of M. Okay, let me write the corollary first. Then the smallest, then the automata number of states in M is at least as large as RL. Further, there is an automata M prime such that L equals L of M prime, and which has precisely number of equivalence classes in RL, number of states. Okay. So first part we showed, in the first part of the Myhill-Nerode theorem, we showed that if M is a finite automata and L is the language corresponding to it, then the number of states in M cannot be fewer than the number of equivalence classes in RL. And the converse part of the theorem showed that in fact this bound is tight, in the sense that if L is any regular language, then you can construct an automata which has precisely precisely as many states as the number of equivalence class in R sub L. So thus the minimum DFA that means the DFA for a regular language L, which has the fewest number of states, has precisely number of equivalence classes in RL, number of states. So what this is saying is that if you come up with any regular language, then there is a smallest DFA which computes this language L, which recognizes this regular language L, and the number of equivalence classes in that is precisely the number of equivalence classes in R sub L. So in some sense, you can think of, if you think of a regular language as a language, and the DFA as a program for computing the language, and the number of states as a measure of the size of the program, then the Myhill-Nerode theorem tells you that the size of the smallest program computing this regular language L is precisely the number of equivalence classes in RL. There's such a characterization, while this basically is something true for finite automata, but such a characterization is missing, certainly missing, and in fact, like, we'll see, is probably impossible to obtain really for richer classes of programs like Turing machines, which you will see later in the course. Okay, so to recap what we saw in this lecture, we started with the definition of RL. Okay, we started with the language L, and we defined an equivalence relation R sub L on the strings over sigma. This is true. This was well defined for any language L, regular or not regular. Then we gave the definition of distinguishable strings. Then, corresponding to finite automata, we defined an equivalence relation R sub M, again over in strings over sigma, where sigma is the underlying alphabet. And then we showed two things. We first showed that if L is the language corresponding to LM, it's corresponding to automata M, so L equals LM, then RM refines RL, which means that if L is a regular language, then consequently you get that RL must have finite number of equivalence classes. And then he showed that if the L is any language which has finite number of, such that RL has finite number of equivalence classes, then it's a regular language. And for this, we constructed the automata. And thus we arrive at the Myhill-Nerode theorem, which says that a language L is regular if and only if RL has finite number of equivalence classes. And in fact, the number of equivalence classes of RL for a regular language L is precisely also the fewest number of states in a DFA computing L or recognizing L. So with that, let me conclude this video.